Okay, so that was the equation for the case of a work of a variable force. But what about the work of a constant force that is moving in a straight line? What would be the equation look like? Again, let's draw a scenario for that case. So we have a straight path for a particle that is moving along that from point S1 to point S2, and let's say this is the force and this is the component of a force. Since this is a constant force, let's just label it F sub C and F sub C here. So again, let's begin with the fundamental equation, which is du F dr or F cosine theta ds. So which one of these equation of work are we going to use? First, let's try the second one, which is this part. So that would be the work from point 1 to point 2 is equals to F cosine theta ds from point S1 to point S2. And since our F is the F sub C, and also because Fc cosine theta is constant, because Fc is constant and the assumed orientation of Fc is the same, then Fc cosine theta is also constant, and we can move it to the left such that the equation becomes Fc cosine theta S1 S2 ds. And now we can integrate this one. This would result to work from point 1 to point 2 is equals to Fc cosine theta, and that would be S sub 2 minus S sub 1, or simply we can write Fc cosine theta delta S. So this is very familiar. We have already seen this one from physics, where we have a component of a force multiplied to the displacement. So this is the equation for a case of a work of a constant force, and we use this equation. But what about if we use this vector notation? What would be the equation? What would the equation look like? The answer is still the same, because our case does not change. It's just a matter of method. But if you want to go in that direction, then we can also provide that path. So let's begin by integration of the work from position R1 to position R2. So first, let's define the F and the R. In order to do that, let's first have a origin. Let's position our origin on the left side, such that we have a position R1 and a position R2. Okay? So for F, let's define F vectorially as Fxi and Fyj. So for differential R, we could write generally as dxi and dyj. But since our position R1 and R2 are in line with x position, then we don't have a dy. We only have dxi. So now we have equations for force and position. We are now ready to plug them in. So this would be R1, R2, and for the F, that would be Fxi, Fyj, dot product of dr, which is dxi. So the resulting equation would be, since the product of I and j is 0, ij is 0 or ji is 0. Since I and j are perpendicular to each other, then the cosine of 90 degrees is equals to 0. So what is now left is the I and I is equals to 1, because cosine 0 is equals to 1. The same with j and k. So the resulting equation is r1 r2 fx multiplied by dx. So now, because our differential is changed to x, our limit should also be changed to x. That would be x1, x2, fx, dx. And this is pretty much the same as the above, only that your symbol or letter is x instead of s, and this would result in a similar equation, which is x, that would be dx. They are just the same. Fx is equals to fc cosine theta, and delta s is equals to delta x. Okay?